Hello, folks. Today I am going to give you an introductory lecture to Shannon capacity formula. During this video, I am expected to derive the Shannon capacity formula and also give a small introduction for mathematical theory of communication and its general capacity formula. And finally, I will give you an concretized example to verify the concept of channel capacity formula. If we talk about mathematical theory of communication, it's an core and basic theory for all the digital communication systems. And, its origin is because of Shannon published a paper in 1948 based on the digital communication, and this is the birth of the information age for this world. So, if we talk about the channel capacity formula, where the channel capacity formula can be represented using this statement, where C is the channel capacity, bit per second, W is the bandwidth of the channel, and SNR is signal to noise ratio. So, these combinations of parameters can be expressed in channel capacity formula. And if we want to derive this or prove the Shannon capacity formula, a proof of Shannon capacity formula can be done using a simplified assumption rather than the originally published by Shannon in 1948 in the mathematical theory of communication. However, let me assume that the band limited, power limited channel into this block diagram. In the block diagram, we have a transmission section and channel and noise generation part, and the receiver and destination message. Also, we can assume that when the digital transmission transmits through a channel, that can be wireless channel or wire channel, right? That can be assumed there exists an signal deformation due to the various kind of reasoning of noises added along the propagation. Therefore, we receive the distort channel at the receiving end. Also, we can assume jumbles of possibilities for digital transmission to message symbols. Let us assume that each message we are sending is B bits long and M number of messages can be decoded at the receiver end, including error corrections. And we can assume that capital N number of messages which can be decoded by any means of the smart code board. Therefore, we can assume there are M plus M number of possibilities for message symbols at the receiving end. And if we consider the power sets of bits, that is nothing but entire message space. or we can modify this statement 1 as we treat logarithmic base of 2, right? So we can able to reach a formulation for total number of bits involved to transmit the n plus n number of messages. Also, we can rearrange the statement as we shown in the statement number 2 for some important derivations, right? Then the reduction of statement 2 can be considered as the next step. So in here we can assume that V0 is the number of bits required to transmit unreadable messages, and we can quantify this relation to V0, and that is the same thing in here. Now if we consider this statement number 3, that is nothing but bits required for error-free communication, right, or decodable messages. Also this H can be considered as the entropy of the digital communication system. In other words, entropy is number of minimum bits required to transmit the error-free message symbols. And now we can further push this derivation as we plug H into the statement number 2, and we will be able to quantify a relation for entropy or minimum number of bits required to transmit the error-free transmission into statement number 4, right? Then we can also derive signal and noise power respect to the average received power at the receiver's end using probabilistic proportions, and therefore we can derive the SNR ratio to statement number 5. Now that is the same as m by n. Then SNR ratio can be plugged to here in the equation, and we can have the total number of entropy or minimum number of bits required to transmit the error-free message symbols into the quantify into the statement number 6. Also, the entropy, amount of entropy is nothing but the ratio to channel capacity to bandwidth. Now H can be substituted into the statement number 6, and we able to derive the channel capacity formula into the statement number 8. And let me give you a small example to concretize the concept. Let us assume that we receive a signal power at about 20 milliwatt at the room temperature, that is at 27 Celsius. Then also we can assume the channel condition of the bandwidth as a 1 megahertz. That is the 1 megahertz of band limited channel. So in the first step, we can assume Shannon-Hartley thermal noise formula to compute the amount of thermal noise, because at the room temperature we have to assume the thermal noises if the other noises are not mentioned. Therefore, thermal noises are can be computed by the Shannon-Hartley thermal noise formula. Here, K is the Boltzmann constant, T is the temperature in Kelvin, W is the bandwidth. Then the noise power can be computed using these relationships. Also, we can compute the SNR ratio as we receive 20 milliwatt to this thermal noise that we earlier computed. Now, finally, we can plug the numbers into the Shannon capacity formula, and we will end up with some number. For this example, we are required about 42 megabits per second for the data transmission at the transmitter end, also data receiving capability at the receiving end. So these are my references to this small lecture, and thank you very much. Please subscribe and make your comment in the comment section.